I'm Connor Logan. This is my glider project final presentation. So project description, the goal was to design a glider that flies as far as possible while adhering to the following requirements. That had to be working by November 14th, being 16 by 16 inches or less when viewed from above, flying at least 20 feet using no form of propulsion, and using mostly the materials provided, that being the balsa plate and square wood dowel as well as the Play-Doh. I'm just going to talk about the design process first. The first thing I came up with alternative designs for is wing shape. So one option would be a square wing. This is very easy to build as well as very strong, but it has relatively high drag. Another option would be just cutting a trailing edge taper into a square wing. Still very easy to build, just one more cut, and has slightly less drag. And a trailing edge taper also offers some passive roll stability, but this still has less than optimal wingtip drag. Finally, an elliptical wing has the lowest drag, but it's by far the most complicated to make with the curved cut. It's also very fragile. You just have lots of end grain exposed at weird different angles. Another design alternative would be wing angle. So anhedral wings can increase maneuverability, but this is actually bad. In this case, we want as much passive stability as possible. They're also difficult to implement. You'd have to print some kind of bracket or mounting interface, which would add weight and would take time to design. So a neutral wing angle is considerably easier to make, and it's also lighter because you don't need a special mounting interface, but it has no special aerodynamic properties. And then a dihedral wing has natural roll stability, which is very desirable, but again, for the same reasons as the anhedral wing, it's difficult to implement. The final design alternative was aspect ratio. So a low aspect ratio wing is durable, but has a pretty poor lift to drag ratio. It also uses lots of material per wingspan. High aspect ratio is pretty much the opposite, very favorable lift to drag ratio, not a lot of material per inch wingspan, but it's pretty fragile. Actually, if your aspect ratio is too high, the aerodynamic forces will just rip your wings off when you throw the glider. So a medium aspect ratio wing would have some serviceable lift to drag ratio and serviceable durability. But the cons are really that it's probably not going to be competition winning because it isn't very specialized. Here's my initial design sketch. You can see I went with the tapered trailing edge and dihedral wings for as much passive roll stability as possible. I also chose a pretty medium aspect ratio. I just wanted to make the aspect ratio as high as possible, where I was still intuitively thought that the balsa wood wouldn't break just from feeling the material properties of it in my hands. This was to get as good of a lift to drag ratio as I could without risking it being just way too fragile. So my first built design, which I called Saucewind, after the first elliptical wing monoplane, I named it that because I actually switched to elliptical wings because I realized we had access to a laser cutter, which negated the difficulty of construction con of the elliptical wing. I also moved the wing root back slightly. This was to get the center of gravity more in line with the 1/4 chord mark. So in testing, this design had very good roll very good roll and yaw stability, but it had a pitch up moment that would lead to it stalling and failing to go 20 feet. So for design improvements, I added some trim to the horizontal stabilizers, as well as a little bit more weight to the nose of the glider. These resulted in the pitch up to stall stopping, which allowed the glider to fulfill the 20-foot requirement. Okay, just to talk about my final design a little bit. The center of gravity is actually a few millimeters in front of the 1/4 chord line, but I couldn't make granular enough changes in weight, seemingly. When I tried to remove a little bit of weight, the center of gravity would end up being behind the 1/4 chord line. I figured in front of it was going to be have more passive stability than behind it, so I erred on the side of it being in front. Excuse me. Here's my lift and drag coefficients. You can see my lift coefficient was 0.254, which is admittedly not great. And then my total drag coefficient, so zero lift drag plus induced, was 0.00284. I used the equations provided in the project description, and here you can see the value of all of my variables in the equation, as well as what units I used for them. So this is my best flight. It went a distance of 31 feet. Alright. So in summary, the project requirements were met. That is to say, I had a working glider by the 14th. It was less than 16 by 16 inches when viewed from above. It went 20 feet and had no propulsion. It used mostly the materials provided. So the project was in 3 phases. There was the research and brainstorming phase of the project, which can be sort of aligned with Glider Checkpoint 1. So the considering initial design alternatives, coming up with some initial combination of alternatives. There's the initial testing and design, which is what we really presented in Glider Checkpoint 2. So getting data back from just initial tests of that design we came up with in the first phase. And finally, there was iteration before final testing, which would be the November 14th fly-off in the Burger Bowl. So these 3 phases together sort of formed a very rudimentary version of the engineering design process. Some farther improvements I would make to my design. I experimented with bending an aerofoil into some scrap pieces of balsa wood. It actually seemed to be possible if you got the balsa wood very wet. I was just worried about it drying unevenly and then warping. But maybe some more experimentation into that would find a reliable way to do it. I'd also move the wing root back a little bit farther just so I could use a little bit less mass on the nose. Finally, in addition to the AE1601 aerodynamics module slides, I also found these 3 articles from the NASA Glenn Research Center website very helpful in designing my glider. All right, thank you.